IGCSE Computer Science, Syllabus Statement 1.1.3e, and this is the same as last time, but we're just going to be continuing this statement. So this video will cover, if I can remember, check digits, checksums, ARQs, and echo checks. So let's start with check digits. So a check digit is the final digit in a code, calculated using all the other digits of the code. So they're used for barcodes, product codes, ISBN, and VIN. And they're used for identifying errors in data entry. So for example, a typo or a scanning error. So they usually can identify an incorrect digit entered, transposition errors, which basically means if you were to type in 2233, but you accidentally typed in 2323, the transposition would be the 2 and the 3 in the middle would be switched. So that's omitted or extra digits. So like if you were meant to type in a 4-digit PIN and you typed in 5 digits or 3 digits. And phonetic errors in speech. So like if you were to say the number 13, and so you said that like you spoke it, but then the computer thought you said 30, then that's it. It's a phonetic error. So an example of a check digit calculation is ISBN 13. So the last digit, the 13th, is calculated like this. So sum all the odd digits, excluding the check digit, sum all the even digits, and multiply by 3. Add the sums, and mod to get the remainder. And modding is basically getting the remainder of a division. So, for example, if you were to mod, so like if you were to do 22 divided by 10, well, 22 divided by 10 would be, I'm just checking that on my calculator. I mean, I know it's 2.2, but I was just making sure. I don't know, I always have this, like, I always have to check before I say something. I mean, I know that it's 2.2, but I always have to check it. So yeah, it is 2.2. But it can also be said 2 remainder 2. So basically, 10 goes into 22 twice with a remainder of 2. So 22 mod 10 would just be 2. So if the remainder is 0, this is the check digit. Otherwise, subtract the remainder from 10 to get the check digit. So we'll look at an example. So calculate the check digit for this code. So an ISBN 13 code, ISBN 12 it looks like now, but you have to, like the check digit would be right here, but we need to calculate it. So let's put it in a table, put the numbers in, and we're going to calculate the check digit. So we first add the odd numbers, and when we say odd numbers, we don't mean the odd numbers, we mean the numbers in the odd positions. So 1, 3, 5, 7, 9, 11, and, well, we're excluding this for now. So it's 1, 3, 5, 7, 9, 11. So 1 plus 5 plus 6 plus 3 plus 6 plus 3 gives 24. And the even numbers, or the numbers in the even positions, times 3. So it's 2 plus 4 plus 5 plus 5 plus 9 plus 6 times 3 gives us 93. And I double checked all of these, so they shouldn't have any errors. If they do, please, like, you know, keep in mind they put a lot of effort into these. No, they shouldn't have errors, hopefully. And we add them, the sums, and then we mod by 10 to get 7. And of course, since 7 isn't 0, we must subtract this from 10. So 10 minus 7 gives 3. So the check digit is 3. So let's try another one. Plug in the numbers. We'll whiz through this because, well, you know, you hopefully know the process of doing this. So there's this, and since this is 0, that's 0, so we don't need to subtract 10 from 0 to get 10. So just to keep in mind, with check digits in the exam, they won't expect you, I'm pretty sure they won't expect you to know ISBN 13. I'll double check that with the recent October-November paper, but what they'll do, or what they tend to do, what they still do hopefully, is they'll tell you how to calculate the check digit for a specific sort of number, so then you can work from the algorithm that they give you. So to check if an ISBN 13 code is valid, we sum all the odd digits, including the check digit, sum all the even digits and multiply by 3, add the sums and mod to get the remainder, and the code is valid if the remainder is 0. So let's give that a try. Is this code valid? Well, we got the check digit now, so it's 13. Plug it in. So 5 plus 5 plus 2 plus 1 plus 5 plus 2 plus 1 gives us 21. And 1 plus 4 plus 5 plus 2 plus 6 plus 12 times, or plus 6 plus 5 rather, I was reading this, times 3 gives us 69. And 21 plus 69 mod 10 gives us 0, so that's valid. Is this code valid? So do the same thing. So we get 19 plus 93, which mod 10 gives us 2. And so that's invalid since this isn't 0. So checksums are a little bit different. Now, this is another method of error detection in data transmission, just like parity checks. Now this method is a little bit more reliable than parity checks because, as we discussed in the last video, parity checks do have limitations. So here, data is sent in blocks, and at the end of each block, another value is added. And this is the checksum. So how a checksum is calculated? Well, it's a simple algorithm. So let's assume the checksum of a block of data is 1 byte, which gives us, gives it a maximum decimal value of 255. As in a decimal value as in base 10. So if the sum of the bytes of the block of data, the sum of the bytes of the block of data is less than or equal to 255, this value is the checksum. If it's higher than 255, then the checksum is calculated as follows. So divide the sum of the bytes of the block of data, we can give the value v, by 256, and we get the value x. Round x down to the nearest integer, so we round it down, which means that if x was, say, 7.3, or rather, actually, let's think of a better one, 7.6, for example, we don't round it up to 8, we round it down to 7. So we basically get rid of what's after the decimal point. So then we calculate z using y times 256, and then the checksum is the original value v minus z. So let's take a look at that with the number 1,223. So x is 1,223 over 256. That gives us 4.78. We round it down to get 4, so we get rid of this. Then we calculate z, which is 4 times 256, and that gives us 1,024. And the checksum is 1,223, which is the original value, minus 1,024, which gives us 199. And as you notice, that's under 255. So before a block of data is transmitted, the checksum is calculated by the sender and is sent to the receiver along with the data. The receiver then recalculates the checksum of the received data using the same algorithm and compares it with the checksum sent. Now, if the values are the same, then there have been no errors in transmission. If they are not the same, of course, the receiver sends a request to the sender to resend the data. So let's look at a question. Calculate the checksum of a block of data with the byte sum 1,805. So it's good to get practice using this algorithm and to memorize it, because if the exam actually doesn't give it to you, then, well, you know, you're screwed. Also keep in mind it's a non-calculator test, so they shouldn't really give you really high numbers, and that's probably why they ask you to round y down, because you know, to make it an integer, so it's easier to work with. You don't have to times the... Yeah, okay, so we calculate x. So x is 1,805 over 256. That gives us 7.05. And we, of course, round it down to 7. Then we do 7 times 256 to get z, which is 1,792. And the checksum, of course, is the original value minus 1,792, and the checksum is 13. ARQs. Now, coming to the slide, we're almost done with the video. We just have to cover two more things, this and echo checks. So an automatic repeat request, or ARQ, is yet another method of error detection in data transmission. If the receiver detects no errors in the data transmitted, it sends the sender an acknowledgement to notify them that the data has been sent correctly. An acknowledgement is basically a message sent indicating successful data transmission. If the receiver detects errors, it requests the sender to resend the data. If the sender does not receive anything back from the receiver before timeout occurs, the data is automatically resent. So that's basically a timeout is sort of a set time allowed to elapse before an acknowledgement is received. And this will keep happening until the sender receives an acknowledgement. That's it. Echo checks. So an echo check is when data sent to the receiver gets resent back to the sender, which checks if any errors have occurred during transmission. Now that sounds a little bit stupid. Like imagine like a device sending data to another device, and that device resends it back so that it can check whether errors have occurred. Now that is quite, it's really unreliable, because they don't know whether the error or an error has occurred during sending the data to the receiver or resending the data back to the sender. So when a device sends data to a receiver, or when a sender, if your computer sends data to a printer, the printer will resend the data back to your computer so it can check. What if the data sent to the printer was perfectly fine, but then when the printer sends the data back, there's an error? So what'll happen is it'll resend it, and then it's really it's not really good. But if it is successful in sending and sending it back, then yeah, it's fine. But still, it's a little bit, yeah. So that's pretty much it for this topic, 1.1, and we're moving on to 1.2, which is the internet, or my friends like to say, the internet. A little bit more than the internet. It's about data transmission itself, as well as security and internet principles. So thanks for watching, and hope you find these videos quite helpful for your revision, or if your teacher forces you to watch them, or whatever happens. I hope you enjoy them. Hope you don't want to kill me, and thanks for watching.